Awesome. Thank you so much for having me. I put theoretical, definitely unobservable ones under the favorite TDEs poll there, so please vote for that one. So I'm a theorist, I'm a dynamicist. I'm from the University of Colorado Boulder. I'm a PhD candidate in my 5th year. I work with Amory Madigan as well as Smadar Naus over at UCLA on the fascinating dynamics that lead to these tidal disruption events. Okay, so this conference has been great so far already for me. And so on the very first day, we had a lot of talks related to host galaxies of these TDEs. And so on the left-hand side, we have the Green Valley galaxies. And on the right-hand side, we have these E plus A, or post-starburst galaxies. Both of these are overrepresented in the TDE host galaxy sample that we currently have. And so this is already an interesting thing to talk about. And so I encourage you, these are, a lot of these are talks that have already happened on the first day. I encourage you to go take a look at the talks by these amazing scientists that do work on this. But essentially, there's a lot of reason to want to look at these galaxy mergers as a way to study the connection between galaxy mergers and tidal disruption events. Okay. So essentially, this gives dynamicists like myself an excuse to go look at galaxy mergers and see what processes go on. So I want to start with this amazing simulation of a galaxy merger. And there's a lot of things that happen dynamically when two galaxies merge. And today in particular, I want to focus on the supermassive black holes that live in at the center of most massive galaxies that eventually should form a binary system. And in particular, if you wanted to study the binary dynamics, you can use this eccentric quasi-Lidov mechanism, which I won't talk about today, but there are talks by Grant Weldon and Denise Melchor from UCLA who are going to talk about the eccentric quasi-Lidov in this context. But today I want to talk about these recoiling supermassive black holes. And so when you have a binary supermassive black hole system, and if there is any sort of asymmetry associated with that binary, it turns out that the gravitational wave signal that you get from the supermassive black hole can carry away linear momentum from the system, and the merger remnant gets a recoil kick. So here is a simulation of a supermassive black hole binary. There is a certain mass ratio, so one is more massive than the other. The supermassive black holes initially also have spin vectors, and as they come in, you can see the gravitational wave contours there. And if there is linear momentum released by the gravitational wave, the supermassive black hole merger remnant actually flies out and gets a sort of impulsive kick. And this is called the gravitational wave recoil kick. And so I and Anne-Marie in particular, we are interested in trying to study these recoil kicks and the effect that this recoil kick has on the surrounding nuclear star cluster. Okay. So a little bit more about the gravitational wave recoil kick, in particular, what we expect the kick magnitude to be. So here is a plot of the kick magnitude on the y-axis in kilometers per second as a function of q, the mass ratio. This is the mass of the less massive black hole divided by the mass of the more massive black hole. And in general, it's going to change as you assume different spin vector orientations of the two black holes. So in the different lines, I've assumed different spin orientations. But in particular, I want to just mention that typically we expect kick magnitudes in this hundreds of kilometers per second range. But in particular spin orientations, we actually get these super kicks of thousands of kilometers per second or more. And in particular, in this case, you can have a recoil that is large enough for the supermassive black hole to be ejected out of its host galaxy and becomes a recoiled or rogue supermassive black hole. And I'll touch on that at the very end of the talk. But for now, I want to focus on what this gravitational wave recoil kick does to the surrounding nuclear star cluster in terms of the gravitational dynamics and the stellar cluster structure. Okay. So before I can introduce what the gravitational wave recoil kick actually does, there is some dynamicist jargon that I want to introduce, and in particular, in our group, we like to make use of this vector quantity called the eccentricity vector. So if you imagine a star in an eccentric orbit around the supermassive black hole, the eccentricity vector is a vector that points from the apoapsis, which is the farthest point in the approach, over to the periapsis, which is the closest point of approach. If you imagine, for example, a symmetric disk where all of the orbits are randomly oriented in 3D space, that means that even if you have eccentric orbits, the eccentric orbits are sort of randomly pointing in 3D space, which means that the eccentricity vectors are also going to point in not any particular coherent direction. But it turns out that this is sort of a spoiler alert, but we are going to get a structure called an eccentric disk when you give a kick. And so an eccentric disk is going to show some sort of alignment between these eccentricity vectors. So you have a cluster of periapses on one side of the supermassive black hole and a cluster of apoapses on the other side of the supermassive black hole. And consequently, you get eccentricity vectors that are going to coherently point in one direction. So this structure is called an eccentric disk, and this alignment is called upsidal alignment of these eccentric orbits. So in particular, we use in our simulations and analysis this quantity called the mean eccentricity vector, which is basically just a vector average. If you imagine adding all of these vectors together, in the symmetric case, the vectors tend to cancel each other out on average, and you get a mean eccentricity vector magnitude that is closer to 0. Whereas in the eccentric disk case, all of the eccentricity vectors are going to coherently add together, and you get, if you have highly eccentric orbits that are upsidally aligned together, you get close to 1. And so mean eccentricity vector deviates toward unity as you get more and more upsidal alignment in your system. Okay, so let's take a look at how this gravitational wave recoil kick causes this eccentric disk to form. And I like to walk through this toy model example just so we're on the same page. So if we just imagine a perfectly circular star orbit initially pre-kick, and if you imagine that the screen is the XY plane, the star is initially rotating in the counterclockwise direction. And let's say that the kick is in the positive X direction in this case. And let's figure out what the post-kick structure looks like. So one sort of straightforward case to look at here is this grain star that's located toward the positive Y direction initially. So initially, the grain star, because it's counterclockwise rotating, is going to be going to have an initial velocity that's pointing in the negative X direction. But now, if you put yourself in the reference frame of the black hole, you just received a kick in the positive X direction. And so the green star in your reference frame is going to actually increase and get a boost in its speed. And so the green star is going to get a boost in its speed and go into a larger eccentric orbit, as shown in the green here, in the black hole's reference frame. You can repeat the same exercise for this orange star down here. So initially, the velocity is pointed in the positive X direction, but now putting yourself in the shoes of the black hole, the orange star actually seems to slow down in your reference frame, and you go into a smaller eccentric orbit, as shown in the orange. And so what you might notice is for both of these post-kick orbits, the green and the orange, you actually have eccentricity vectors that are coherently pointing upward, so in the positive Y direction in this case. And you can actually repeat this sort of analysis for all circular orbits, regardless of where the star starts initially on its orbit. And if you do that analysis, you get this nice equation where the mean eccentricity vector is expected to be 3/2 times the kick velocity divided by the star velocity, v star, initially. And so this gives you a sense of how much alignment you expect when you start with a circular disk, where the star's velocity is such and the kick velocity is such. Okay, so that's the analytic expectation, but we wanted to recreate this with n-body simulations, and in particular, we use this n-body package called Rebound. And when you do that, and initially we have a circular disk around the supermassive black hole, and if we give the same sort of condition of a kick in the plane of that disk, starting with a circular disk, indeed, in n-body simulations, you form this eccentric disk where you have an alignment, a coherent alignment, perpendicular to the kick direction in this case. Okay, So I just walked you through essentially the formation mechanism of eccentric disks. But what does that have to do with tidal disruption events? And so what are some of the expected tidal disruption event rates that you can get from these recoiling supermassive black holes once you form this eccentric disk? So here's how we detect tidal disruption events in our simulations in Rebound. Currently, we use a feature called collision detection in this n-body simulation, where we give the supermassive black hole a tidal radius, and whenever a star comes into this tidal disruption radius, Rebound has a feature to be able to detect this star as it's entering this tidal disruption radius as a collision. And so we can actually track the orbital parameters of this tidal disruption event in our n-body simulations this way. Okay, so when we do this analysis and detect the tidal disruption events in our n-body simulation, we can plot in our simulation the tidal disruption event, how many stars in our disk is going to be tidally disrupted over time in our simulations. And when we do this analysis, we get something like this. And so within 16 mega years or so, in this case, 15% of the disk is tidally disrupted. And I want to emphasize that you're not reading the y-axis incorrectly. So we predict extremely, extremely high tidal disruption event rates from our simulations. Up to an order of 0.1 per year per galaxy or so is what you get initially in this initial burst of tidal disruption events that you can get from forming this eccentric disk from a gravitational wave recoil kick. Okay, so why are tidal disruption event rates so high in eccentric disks? And so that's related to how the eccentric orbits in an eccentric disk evolve together. And so here in this animation, I'm schematically illustrating an individual orbit within the eccentric disk in the red, and sort of the average body of the eccentric disk in the thicker white line. And we are going to see how this is going to evolve dynamically together. So I'm going to let the movie play once through, and then I'm going to explain what's going on in terms of the dynamics there. So once again, the thicker white line is showing the motion of the average eccentric orbit within the disk, whereas the red is just an individual orbit within your eccentric disk. Okay, so as it comes around, I want to explain what's going on. And so let's stop right there. So in general, in dynamics, circular orbits tend to precess faster than eccentric ones, and this is because the circular orbits have shorter eccentricity vectors. Precession is the rate of change of the eccentricity vector. So basically, the circular orbits are easier for you to torque. So initially, the red orbits started out being more circular than the average eccentricity that exists in the disk. And so the red orbit has precessed slightly ahead of the mean body of the eccentric disk. But in this case, what happens is that because all of the orbits are aligned and eccentric, most of the mass in stars are actually located near the apoapses, where the stars spend most of their time. And so there's a very strong torque that is felt by the red orbit. So in this case, it's a negative torque. And negative torque decreases the angular momentum, which actually increases the eccentricity of this orbit. And so it works to slow the orbit down until now the red orbit has lagged behind the mean body of the eccentric disk. And the exact opposite happens dynamically. And so you have a positive torque that is now felt by the red individual orbit, which is going to increase its angular momentum, decrease its eccentricity, and you get this oscillatory behavior where the red orbit is sort of precessing ahead and lagging behind, and precessing ahead and lagging behind. And at the same time, you get these really extreme eccentricity oscillations. So the orbit also becomes eccentric and circular and eccentric and circular as it evolves in this eccentric disk. Okay, so the result of this, if you track the tidal disruption events in our simulation, so I've selected 4 sort of representative tidal disruption event stars in our simulation. And on the y-axis, I'm plotting 1 minus eccentricity on a log scale. So as you go downward in this plot, you get more and more eccentric orbits, and time on the x-axis. And you can see that these 4 representative stars in our simulation are undergoing these extreme eccentricity oscillations caused by the torque picture that I showed in the movie in the previous slide. And so as these stars become torqued to extreme eccentricities means that you approach closer and closer to the supermassive black hole, and you get tidal disruption events to happen more efficiently than symmetric configurations in our simulation. Okay, the final thing that I wanted to go through related to kicks is the fact that there is a dependence, a very strong dependence of where the eccentric disk is going to form given a kick of a certain magnitude. And so here I'm showing essentially the radius out in the simulation that I go and the alignment on the y-axis. And so as you go from weaker kicks to stronger kicks, you get stronger upsidal alignment closer in. And so if you take a look back at the analytical formula that I showed, it actually makes sense. So if the alignment that you expect is 3/2 v kick divided by v star, and v star is square root of gm over r, you can rearrange to show that it scales as gm over v kick squared. And so there's a very strong dependence on the kick magnitude. And so in particular here, if you go from 120 to, for example, 1200, which is a factor of 10, you're decreasing the radius at which you expect this alignment by a factor, by 2 orders of magnitude in this case. Okay, so this super kick regime, where you get thousands of kilometers per second recoil kicks, are really interesting in this way. Because you actually form an eccentric disk that is really compact and really close to the supermassive black hole. And so these are very preliminary results from super kicks, but in this case I gave the supermassive black hole a kick of 1,500 kilometers per second. And what you can see here is that, and this, obviously the scaling here is kiloyears, so this is less than 0.1 megayears that's shown on the x-axis here. But roughly 50% of the stars get tidally disrupted within this short time scale. So this is both good and bad, right? So if you're thinking about off-nuclear TDEs or extragalactic TDEs, maybe this is showing you that you're actually going to eat most of the stars before the supermassive black hole makes its way sufficiently out of the galaxy. And so that might be bad news from that regard. But in terms of dynamics, it's super cool. So 50% of stars get tidally disrupted within 0.1 megayears, which is a ridiculous burst of tidal disruption events. Okay, and so this is slightly off topic, not particularly related to TDEs, but I'm also a dynamicist who likes to study kicks and what happens dynamically in general. And so I have a paper out from last year looking at essentially. Today, I only walked through the very specific case of a circular disk and an in-plane kick. But in general, you can get a lot of different post-kick structures. So if you have an out-of-plane kick, it turns out that you get this sort of eccentric torus where all the orbits are coherently tilting over their major axis. We looked at the eccentric disk case in particular today. But it turns out that when you have a disk with initial eccentricities, you can also form really fascinating structures, like the double eccentric nuclear disk where you have 2 eccentric nuclear disks. And even if you start with the most general configuration of a thermal eccentricity distribution and a spherical ball of stars, you actually still get this sort of weird toroidal structure where the eccentricity vectors are all concentrated in one plane. And so more simulations are necessary to study these cases, but I'm fascinated by these as well. And I also have a very recent paper that just got posted on the archive, which is actually applying the same mechanism to white dwarfs and planetesimal tidal disruption events around white dwarfs. And so I'm really interested in this project as well. If anybody else in the audience is interested, please come talk to me about that. And in the last couple of minutes, I just wanted to shout out, I'm the only one, unfortunately, from the Madigan group at CU Boulder here at this conference. So I wanted to just highlight a couple of people in particular. So Jane Bright is a finishing grad student. And so she's on the job market right now, and she's also working on this fascinating problem of kicks. She's in particular working on prograde versus retrograde orbits in the context of eccentric disks. And the white dwarf project that I mentioned in the previous slide was in collaboration with an undergrad, Sayla McIntyre at CU Boulder, who is graduating and will be applying for grad schools in the fall as well. So I wanted to highlight those 2 people in particular from my group. Okay. And finally, I wanted to just share future work very briefly, where I made this plot recently and I started to populate this plot So in the x-axis, I have essentially the mass of the central object, and on the y-axis, I have the kick that's expected. So it turns out that in astrophysics, kicks are fairly common, and there are kicks of various magnitudes that are imparted on central objects of various masses. And so I started to populate this plot where you have kick magnitude versus the central mass. And so you have supermassive black hole recoil, white dwarf natal kick, supernova kicks, stellar mass black hole recoil, and intermediate mass ratio in spirals. And so you can start to populate this interesting parameter space here. And so it's a dynamically very rich and interesting field. Okay, so I'll leave my key takeaways up there and give you a chance to scan the QR codes of the papers here in case you're interested in reading them. Thank you so much, and I'll take questions.
Okay, so I have a question. So you showed how the secular evolution between the eccentric disk and one of these stars could excite it to arbitrarily high eccentricities, but have you considered the GR precession and the so-called Schwarzschild barrier, which might hinder that process?
Yeah, so our group, not me, but an older grad student that Anne-Marie worked with, she considered GR precession and showed that the tidal disruption event rate that you can get from eccentric nuclear disks don't differ between the Newtonian case and including GR precession. And so, yeah,
this statement will probably depend on the mass of the supermassive black hole.
Yeah, absolutely.
How relativistic is the orbit around the tidal radius, right?
Of course, yeah. So in general, obviously, GR makes it a little bit more computationally expensive, but we try our best to justify using timescales that GR precession doesn't play a strong role in this process, and the secular timescale is much shorter than the GR precession timescale. And so in an eccentric disk, you should see these tidal disruption event rates at roughly the same time, regardless of whether you take into account GR or not. But thank you for the question, yeah.
Great. Go ahead.
Yeah, that's a great question. So it does very much depend on the spin alignment, and my understanding is that it's really hard to constrain the distribution of spins that exist in supermassive black holes. But the general picture that I have, this is a naive picture, but when you have roughly equal mass a supermassive black hole, if it's a non-spinning case, you don't actually have asymmetry, so you don't get a kick. And obviously, on the other end, you have a situation where the mass ratio is too extreme for the supermassive black holes to get a kick. So there's sort of this sweet spot in the middle where I believe the mass ratio is like 3-to-1 or 4-to-1 or something like that, where you can expect this substantial kick to come out of it. So that's an interesting problem, and I need to kind of fill out this parameter space and study it a little bit more to be able to say if there's a definitive time scale that you expect this, post-starburst phase where you expect this enhancement of TDEs. But yeah, great question.
Thanks for the great talk. So imagine you have a very strong kick. I can imagine that sometimes it may actually combine some of the stars orbiting the black hole. So is that going to suppress the efficiency to generate TDEs?
Absolutely. So the equation that I showed was basically the fact that the radius at which the eccentric disk is expected to form scales as v kick to the -2. And so as you have super kicks, you are essentially making the stellar cluster more and more compact. And so depending on the density distribution that you assume initially, even though nuclear star clusters are extremely dense, you are basically selecting a very compact star cluster that is flying out with the supermassive black hole. And our simulations have shown that you do need sufficient mass around the supermassive black hole. In general, we need about 1% of the supermassive black hole mass to be in the stellar disk around it for sort of this mechanism to work. And so that's something that we have to look into it a little bit more. So if there's not enough mass in stars, the torques are not strong enough that the eccentric disk is not able to hold itself together, and the TDE rates are not enhanced to the extent that I'm showing in this talk.
So the fraction of TDEs you're showing there by counting the fraction of TDEs compared to like the number of stars like before the peaks. It's not just the number of stars that remain in the system.
It is counting just the number of stars that remain bound in the system, but the total mass that exists in the bound system does depend very strongly on the kick magnitude, is my point. So
that's why I say in your plot that for very strong cases, ratios will become very large, but actually there might be a lot of mass that's already lost.
yeah, exactly. And there is, so initially we assume typical nuclear star densities, right, of 10 to the 6, 10 to the 7 per cubic parsec. And then we see what, we assume a density profile that's cusp-like or core-like. And then we say, okay, this is the radius at which you don't expect bound stars anymore. And this is the system that is bound and forms an eccentric disk. And we just count the fraction of that bound system. So yeah, we're absolutely not taking into account the unbound system after we've determined that it's unbound from the black hole. But you're right that there could be sort of effects related to the unbound system as well that we're not taking into account.
Imagine you have a case you have like 10 stars, you don't bound by none of them, and the other one you have the TDE. And you say it's 100% TDE, but actually it's like 1 in 10, something like that.
Yeah, exactly.
Yeah. Okay, I just want to check it. Thanks, great talk. So I have a question about the alignment and eccentric. So does that promote formation of like binaries, for instance? And how are like weird TDEs that for binary structure?
Oh, are you thinking about the like Hill's mechanism, for example, or?
Or yeah, or you can disrupt two stars at the same time. It's like really tight.
Yeah, so far we've only looked at single TDEs. So we're not, going to our simulations and, for example, counting the number of binaries that form or anything like that. But that's definitely an interesting area. Another area of where this is interesting is, for example, in collisions. I haven't looked at collisions between stars in our simulations because in n-body simulations, typically the stars are point particles and we don't detect the collisions between stars. But that's another interesting area because there's a lot of alignment of eccentricity vectors going on, and you could have, right, these high energy phenomena that are not TDEs that are happening in eccentric disks. Yeah. Yeah, great question. So I would love to talk more with observers in the crowd, for sure. But my kind of very speculative theory is that if you have a rate as high as 0.1 per year, that might look like a crazy changing look AGN or changing look, and when it sort of settles down to a rate of around 10 to the minus 3 or so is when you sort of get this post-starburst phase after the merger. That's sort of a really naive picture that I have right now. So I would love to talk to observers with you about how to sort of actually go look for these high TDE rates that you might get from eccentric disk post-kick. Thank you.
Have you considered the tidal distribution in your orbital calculations? If you go back to the eccentricity evolution plot, you can see that eccentricity go up to 0.999, and I think if you consider the tidal distribution in your orbital calculation, the eccentricity will cap. Will be capped at probably only 10 to minus 3 or something like that, so the TDE because it's probably much lower.
Yeah, I have not considered it. Maybe we can talk because I don't have a good answer for the question right now. But yeah, thank you.
Okay, so let's thank Tatsuya once again.